In 2027, something unusual may happen above our heads. Instead of another satellite or telescope, Google plans to test something far more ambitious: AI computing in orbit. Project Suncatcher is not science fiction or marketing hype. It is a real experiment with real hardware and a real launch timeline. The question is simple but powerful. Is this just a bold test, or the first step toward moving AI infrastructure off Earth? Section 1. Why Project Suncatcher is a turning point for AI infrastructure. Project Suncatcher matters because it turns a long-discussed idea into a scheduled experiment. For years, space-based computing was treated as a theoretical concept. It appeared in research papers, startup pitches, and conference panels, but rarely with clear hardware, timelines, or mission details. Google changed that. It publicly confirmed a plan to launch 2 prototype satellites into low Earth orbit in early 2027, carrying real AI processors and real workloads. What makes this attempt different is Google's decision to rely on existing technology rather than exotic space-only hardware. The satellites will use Google's own TPU chips, the same processors that already power large-scale AI models like Gemini. Instead of redesigning everything from scratch, Google wants to find out whether proven Earth-based AI hardware can survive the harsh environment of orbit with minimal modification. That choice signals confidence and pragmatism, not speculation. Another key shift is the orbital strategy. The satellites will fly in sun-synchronous orbits, meaning they pass over Earth at roughly the same local time on each orbit. This allows them to receive near-continuous sunlight, dramatically increasing available solar power compared to ground-based systems. Without clouds, atmosphere, or nighttime interruptions, each solar panel can deliver more consistent energy than its terrestrial counterpart. Equally important is networking. Project Suncatcher relies on laser-based optical links between satellites, allowing them to exchange data directly at very high speeds. Instead of routing everything through Earth, the satellites can function as a connected computing layer in space. This architecture resembles modern data centers more than traditional satellites. Section 2. The hidden engineering challenges that will decide success or failure. Despite its promise, Project Suncatcher faces obstacles that are far more complex than simply launching hardware into orbit. The most immediate challenge is durability. Space is filled with radiation from the sun and cosmic sources, and electronic components degrade over time under constant exposure. While Google has tested its TPU chips using proton beams on Earth, long-term reliability in orbit remains uncertain. Surviving weeks or months is very different from operating steadily for years. Thermal control is another major hurdle. On Earth, data centers rely on air or liquid cooling to remove heat from servers. In space, neither option exists. Heat can only be expelled through radiators, which must release energy as infrared radiation. These radiators quickly become large and heavy, often accounting for a significant portion of a spacecraft's total mass. Studies by space agencies show that at higher power levels, radiators can represent over 40% of the system's mass. Designing a compact solution that keeps powerful AI chips within safe temperature limits is one of the hardest problems in the entire project. Networking adds another layer of difficulty. Laser communication between satellites requires extreme precision. The beams must remain aligned while both satellites travel at thousands of kilometers per hour. Orbital drift, vibration, and thermal expansion can all disrupt these links. Even brief misalignments can reduce data rates or interrupt communication entirely. Maintaining stable, multi-terabit connections over long periods is an unsolved challenge at this scale. Finally, there is the issue of maintenance. Earth-based data centers are constantly upgraded, repaired, and optimized. In orbit, physical intervention is costly and complex. Any failure must be tolerated, repaired remotely, or addressed through replacement launches. A single weak point can shorten the lifespan of the entire system. Section 3. Economics, scaling, and what success would actually mean. Even if Project Suncatcher works technically, the larger question is whether space-based AI computing can ever make economic sense. The answer depends less on processors and more on launch costs. Today, sending hardware into orbit remains expensive. Google's own research suggests that space-based data centers only become competitive if launch costs fall below roughly $200 per kilogram. That level would require major improvements in launch efficiency and reuse over the next decade. If costs do fall, orbital computing would not replace Earth-based data centers overnight. Instead, it would likely supplement them. Space-based systems could handle energy-intensive workloads during peak demand, reduce strain on electrical grids, or serve regions with limited infrastructure. They might also support applications that benefit from proximity to space assets, such as satellite data processing or large-scale Earth observation analysis. Environmental considerations also play a role. Traditional data centers consume vast amounts of electricity and water for cooling. Space-based systems avoid many of these constraints. Solar power in orbit is abundant, predictable, and emissions-free. While launches themselves carry environmental costs, long-term operation could offset some of the pressures currently faced on Earth. Competition is already forming. SpaceX has publicly discussed future satellites capable of onboard processing, and startups like StarCloud are developing GPU-equipped platforms designed specifically for AI workloads in orbit. Google is not alone, but it is currently the most transparent about timelines and goals. If Project Suncatcher succeeds, it will not announce a new industry overnight. Instead, it will quietly confirm that orbital AI infrastructure is technically feasible. That validation alone could reshape long-term planning across the tech sector, influencing how and where future computing capacity is built. Project Suncatcher is not about abandoning Earth or rushing AI into space. It is about testing whether the boundaries of computing can expand beyond the planet at all. A successful 2027 mission would not solve every challenge, but it would answer one critical question. Can modern AI infrastructure function reliably in orbit? If the answer is yes, the future of computing may become more distributed, more resilient, and less tied to Earth's physical limits. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries, and don't forget to leave a comment below. Thank you for watching, and see you next time.